This is the short summary for Chapter 3 of the functional programming tutorial. Chapter 3 came in 3 parts and 2 addenda. The focus of Chapter 3 is to explain the logic of types. Types play a very important role in functional programming. It might be unclear why logic of types, and this is also part of the focus of this chapter. To begin, we consider functions that return functions. What do these functions look like as an example? And I show why the functions must logically look like this, like functions that are applied to 2 sets of arguments. And then I motivate why the type of these functions is written in this kind of syntax, which looks unfamiliar, perhaps, and strange at first. But this is a very important part of the logic of types. It must be like this, and I explain why. This convention actually is very natural and follows from the logic of what it means to return a function. I give examples of functions that have fully parametric types. I explain what that means. It's a function that manipulates values of unknown types, and types are given as parameters. So I show the Scala syntax for this and explain how that works. I give more examples of functions whose arguments have parametric types. The worked examples is the important part of this lecture that goes in detail through the Scala code of each of those functions, such as const, id, as defined previously. And it gives further examples, such as this function that applies a given function twice. It's important to go through these examples, which are fully explained in the lecture, because it shows how the functions that take functions as arguments can do very non-trivial and interesting things very easily. Another thing I explain is how to infer types. If you just have code like this, you can infer what types these functions must have and what type parameters they must have. This is also a very important part of reasoning about code. It's reasoning about what types various values must have and what are the type parameters. I show that in certain cases expressions cannot be well typed. They cannot have consistent type, but others can. And I give exercises that are very similar to the worked examples, and they're important to follow and to do on your own. The second part of Chapter 3 focused on disjunction types. Before looking at disjunction types, I explain case classes, the so-called case classes in Scala, which are basically the same as tuples except with names. So there are tuples such that each part of the tuple has a name, and also the tuple as a whole has a name. So this is an example where each part of the tuple has a name, and also the tuple as a whole has a name. So the type of the tuple with names is called a case class type. I give examples of how to work with case classes. And I give examples of case classes or tuples that have 0 elements, 1 element, and 2 elements, and how they could be defined as tuples or defined as case classes. And a very important type called unit is essentially equivalent to a tuple with no elements, or equivalently it can be named tuple with no elements, or named unit. To work with case classes, I show pattern matching syntax on examples and explain how pattern variables work in pattern matching. And then it prepares me for explaining disjunction types. So disjunction types are types that describe disjunctions, logical or set disjunctions of domains. So for instance, a value that's either one kind of value or another kind of value or another kind of value. Each of the parts of the disjunction is a different type on its own, and there is no mixing of them. So for example, it's either a point on the line or a point on the surface, but it cannot be both. And then you have mathematically this kind of domain versus a union, but the union has no points in common. So in order to emphasize this, we put names on each part of the union, and so it's always exclusive OR, and these names or labels must be different for each part of the disjunction or union. And that's how functional programming treats these disjunctions. So I explain this in detail. I show now how pattern matching is used to work with these disjunction types. For the example of the either type, which is the simplest standard disjunction type that has a left and the right parts. And I show that this is similar to just a case expression that chooses different possible values of a given type. And here there are two possible domains, which I then show on an example. More generally, you can have, of course, more than two different domains. And in Scala, this is implemented using this syntax, which is verbose, but I explain in detail how this syntax works and how the pattern matching will work. So there's a name for the entire type, there's a name for each part of the disjunction, and then there are names for each parts within each disjunction. I show on an example how one can use the option type, which is perhaps the most often used standard library type, that is a disjunction. So this is an example of how we could divide numbers safely, where division by 0 is excluded from the domain. It's a different domain which has an empty result. And I show that option has many helpful functions that you can use to work with it. I give a lot of examples of using disjunction types and how to define them according to each problem at hand. For example, how to implement functions like this, and how to use disjunction type to represent, say, different days of the week or different cases of solution of a quadratic equation. And I give exercises that are similar to these worked examples. In the third part of this chapter, I discuss the Curry-Howard correspondence, which is an important idea that is based on the types that we have seen so far. We have seen a type parameter, we have seen a tuple, we have seen a disjunction type, a function type, a unit, and also a nothing type, which is new in this part of the chapter 3. And the idea is that each of these type constructions corresponds to a logical proposition that claims that a value of this type can be computed in the code. And I show that there is a one-to-one correspondence between different logical operations such as AND, OR, implication, true and false, and these type constructions. I also show my short notation, which is something I will be using extensively in this entire lecture series. And I give examples of how to write type notation for a function in the Scala syntax and in the kind of mathematical short syntax that I'm using. Now, to explain this in a bit more detail, I show how the Scala syntax for disjunction types corresponds to the short mathematical syntax. My syntax for type parameters is the superscript. So all the type parameters in Scala, they have to be listed like this. I'm just listing them as superscript. The key idea of the Curry-Howard correspondence is that any logical formula that is valid, which is to say it is a theorem of logic, can be implemented as a function with fully parametric arguments, whereas formulas that cannot be implemented correspond to non-theorems or incorrect logical statements, invalid formulas or invalid theorems. And I give examples of valid and invalid formulas and explain how they work. And so then it would be an interesting question to ask, what is the code that corresponds to a logical formula, which is the same as to say, what is the code for a function of a given type? So for a function of type like this question is not very obvious. But there is a decision algorithm, which I show by way of examples. Another question that the Curry-Howard correspondence answers is what are type isomorphisms or equivalences of types. Now, if you map types to logical expressions, then you can ask what are identities of logic. And I wrote here identities using the notation of logic. Identity of logic corresponds to two functions, but they do not necessarily mean that types are equivalent, because these functions can convert values between types, but not necessarily isomorphically. In other words, they could lose information. And so I define isomorphism as two functions converting between two types in both directions that do not lose information. I give examples of types that are isomorphic and types that are not isomorphic or not equivalent. It's the same thing, equivalent and isomorphic. And all these examples I give in Scala and explain how they work. So some of those are logically correct, but they lose information, and so they do not actually give isomorphism of types. And I noticed that this is not an arithmetic identity. This is a logical identity, but if you write it in arithmetic notation like this, it's obviously not equal. And I explain why that is so, why it is so that arithmetic identities corresponds to type isomorphism, and I give more examples with function type, which arithmetically correspond to powers. So power identities like these are standard identities of arithmetic. They correspond to type isomorphisms. I show how that works. To summarize this, I talk about exponential polynomial expressions, that is, expressions made up of variables and operations plus, times, and implication or exponential in the arithmetic. So these are exponential polynomial types that are made out of these operations. And algebraic types, what people call algebraic types, is actually polynomial types. That is, types made only out of these two operations without this. So I introduce this terminology. I show how high school algebra can be used to reason about types in an interesting way, in a visually suggestive way, to understand what are the possible values of a type. For this example, I use the recursive type. And I go through a bunch of cases where I implement functions using their type, or I show that they cannot be implemented, or I transform types into isomorphic other types. And these are exercises that are similar to the worked examples. Finally, I comment about the significance of the Curry-Howard correspondence for programming language design. I show that if a programming language follows the Curry-Howard correspondence, then it is more powerful, and mathematically it means that its logic of types is complete and it's free of inconsistency. And I show that languages like these are mapped to incomplete logics because they do not have the disjunction type and did not have a true and false types, and these are also mapped to very poor logics, and so that is to be seen as a defect. So that's why these languages are less powerful than these in the sense of functional programming. I summarize by saying that there are algorithms that generate code from types and also infer types from code. We can decide the type isomorphism and simplify type formulas, but there are certain problems we cannot solve, which I comment on. And as an addendum, I give some remarks that did not make it into the lecture.